So this is the water cycle. We know what is the water cycle, we have some background on it. And if we look at the river flow, and it is also called surface runoff. Actually, surface runoff is something wider than river flow, because surface runoff is water that flows over the ground. So the ground may be also the hill slope, not necessarily a river, but the surface runoff eventually gets concentrated into a river. So, how is surface runoff originated? By some water contribution in the form of precipitation. So there is precipitation. Precipitation includes rainfall and snow. Rainfall then may infiltrate or may flow over the ground. If the ground is impervious, like a roof or a house, you have water flowing directly over the ground, or it may infiltrate in the shallow or deep underground, and then at the end of the story, this water gets at the earth's surface and flows into the river. If it falls in the form of snow, the process may be delayed. So snow is first accumulated, and when the temperature increases, then you have snow melt and then the surface runoff. If there is infiltration and water doesn't eventually come again to the surface, then this infiltration recharges the aquifers. Let's concentrate for now on the surface runoff. So there might be infiltration, but after a while water comes up again at the Earth's surface and concentrate into the rivers. And later on we will talk about aquifers, how to model aquifers. So this is the process, based on our understanding. So there is an input. What is the input? The input is rainfall, the input is precipitation. And if temperature is relevant, the input is also temperature. So this is our input information. Temperature is always relevant because it may originate snow melt and it may originate evaporation and transpiration. What is called evapotranspiration, the merging of these two processes of evaporation from liquid surface and the transpiration from the plants. Temperature affects evapotranspiration, and therefore temperature is always relevant. In some conditions, the effect of temperature may be neglected. And therefore, while precipitation is an input that is always present, if we want to model this process originating runoff, precipitation is an input that is always present, temperature may be in some cases discarded. When we think that evapotranspiration is negligible, when we think that there is no snow melt, we may discard the temperature. In some cases we do that. So this is our input information, and then there is some other information that we need, like, for instance, the land cover, like the geology. If we want to reproduce this process that originates surface runoff, we need to know whether the Earth's surface is impervious or not. We need to know whether there is infiltration, seepage or not. So we need also this kind of information. In some cases we may neglect it. We may adopt a simplified approach, neglecting this kind of information, but if we want to be rigorous, clearly we need some additional information besides what are dynamic inputs. Dynamic inputs are inputs that are varying in time. Precipitation, temperature. There are other inputs that are not dynamically varying in time. They are fixed, like geology. Land cover may change, but let's say that it's more static with respect to precipitation. So we need some information, and then if we have this information, we may try to elaborate a mathematical tool that reproduces this process of surface runoff. If we are successful in doing that, we can estimate river flow in this way. In this deductive way. This is called, in technical terms, rainfall runoff modeling. Sorry. I said that this is, okay, it is getting, I need to connect to the power, otherwise it blocks the screen. Just 1 second. This is, as I said, an exciting topic, and what is the reason why it is exciting? First of all, because it is potentially able to provide a very exciting solution to the problem of estimating water resources availability. Estimating water resources availability, as I told you, is a huge problem, and which cannot be completely solved by using observations, because we don't have many river flow observations. If we were able to reproduce this rainfall runoff process, of course it is exciting. It is also exciting because it's a problem that is not completely solved. Keep in mind that rainfall runoff model were introduced, conventionally we say that the first rainfall runoff model was the unit hydrograph, which probably you studied already in another course, but we don't care about the unit hydrograph. It was proposed in 1932. What I care is about the date. It was less than 100 years ago. Actually, some people say that the first rainfall runoff model was a rational formula, which I will talk to you about in a few minutes, which was proposed in 1859. But as you will see, the rational formula is very simple. The first elaborate model was the unit hydrograph, the first complex model, let me say this, and it was in 1932. And the models that we use today were all proposed, most of them were proposed after 1970, and the majority of them was proposed after the 90s. So you see that it's a young science. It's a young science because water resources management is a young problem. As I told you, water resources management was introduced in the 70s of the past century. So you can understand why these models are young. And therefore they are still evolving. And this is a very active field of research. Unfortunately, it is very active also because we are not happy. We are still not happy with the performances of these models. And this is why it's also an exciting problem. How can we do that? When we listen people talking about mathematical model, we get a little bit scared because we think of very complicated approaches. And we should remove this concern from our mind. Mathematical models can be very simple, and mathematical models are just what we are used to deal with as engineers. We should get very familiar. There is no reason to be concerned. Like there is as well no reason to be concerned by statistical models. You should, in a way, getting your mind free from these concerns. And in order to try to remove these concerns, I would like to introduce you mathematical models in a very technical way. So what is a mathematical model? It is, everything is described in my pages, so don't worry about, I'm talking and you don't see on the screen a perfect correspondence between my notes and what you see there, but everything is reported in my web pages. But let me say, mathematical models are just systems of equations, and we are used to deal with systems of equations. And they are built by equations. I call them constitutive equations, and they build the model. How many equations? The equation must be, the number of equations must be commensurated to the number of the variables that we want to simulate. And therefore you need a minimum number of equations which is equal to the number of unknowns. And these models typically are dynamic models, they evolve in time. Because the process that we want to describe is a process that is evolving in time, and therefore variables are typically functions of time. Not only functions of input variables, but also function of time. So river flow is a function of rainfall, but it's also a function of time. And therefore, we say that it's a dynamic model. So the first thing that we have to do is to estimate the number of the variables that we want to simulate, estimate. In this case, it's just one, river flow. It's a variable that is evolving in time, in general, but it's one. So one may say, okay, just give me one equation. It could be, but you have to take into account that in order to simulate the variable you are interested in, which is the river flow, you may need to consider the state of the system. And I want to be clear about this. What does it mean, the state of the system? Think about a river basin, a catchment, and think about rainfall. If it rains over a catchment that is dry, or if it rains over a catchment that is completely saturated, it's wet, of course you expect a different river flow. If it rains on the wet, there is a proverb that says that it's a disaster. If it rains on the dry, it's more affordable. So what is the difference between wet and dry? The state of the catchment. The state. So catchment is dry is one state. The catchment is saturated is another state. So when we talk about state of the system, we just talk about something that tells us how the catchment in this case is. So next question is how to quantify wet and dry through a variable. And the variable may be the storage. Water storage. So let me use the blackboard to do this. So let's start by considering a catchment. And let's look at a catchment from the top. If you look at a catchment from the top, you typically see an area which is bounded by a closure section of the catchment, which is a river cross section. And this is the area such that catchment. What is a catchment? I think I already introduced it, but anyway, it's the area such that the rainfall, and only that one, I will repeat later, is the area such that the rainfall that falls over it contributes to the drainage, to the river flow at the given river cross section. So again, it's the area such that the rainfall that falls over there, and only that rainfall, contributes to the river flow at the closure section. Closure. Remember that you have to say the area and only that area, because this makes the difference between, if this is the river, you can identify sub-catchment. This is a sub-catchment, and the sub-catchment the difference between the catchment and the sub-catchment is that the whole area of the sub-catchment contributes to the river flow and the closure, but not only that area. There is additional area that contributes to the river flow here. So when you define an overall catchment, you have to say that it's the area and only that area, such that the rainfall that falls over there, or you may say the precipitation that falls over there, contributes to the river flow at the closure section. Okay. And of course you can visualize here the river network at a certain resolution. Keep in mind that the river network, when you depict the river network, it's always associated to a certain resolution. If you increase the resolution, you get another river here. And if you increase the resolution again, you get another river here. So any representation of the river network is associated to a resolution. Okay, so this is the catchment from the top. And I need to quantify the state. I need to say if it's wet and dry. So let's make a conceptual association between the catchment and the bucket with a closure section that we may represent as a bottom discharge. And in this bucket we have rainfall as a function of time falling into it. And therefore what happens? It happens that rainfall originates a storage. I can call it as W. Storage, the amount of storage, quantifies the state of the catchment. If the storage is zero, the catchment is dry. If the storage reaches its maximum potential value, the catchment is saturated. And therefore, what is storage? It's an additional variable that it's quantifying the state. Storage is a state variable. It's not an input variable. Rainfall is input. River flow, let's call it Qt, is the output. And the storage is a state variable. So in this kind of conceptual model, conceptual means that is mimicking the reality. In this kind of conceptual model that I'm writing here, there are three types of variables: output, input, state. You see that the introduction of a state variable is necessary if I want to take into account the state of the catchment. I may decide to adopt a simple model that does not take into account the state of the catchment. If this is the case, I remove the state variable, and then I end up with only one unknown: river flow. The input I assume that is known. And therefore, only one equation suffices. It's enough. But if I want to take into account the state of the catchment, I need to introduce this state variable, which is an unknown. And therefore, I need two equations. If I want to take into account the ecologic state of the catchment, I may need, just to make an example, ecologic state, just to make an example, I may need an additional state variable, and then an additional equation. If I want to take into account the biological state of the catchment, maybe another state variable. You see that I may increase complexity, and increasing complexity means that I want to take into account other states of the catchment, and therefore I need to introduce additional state variable, additional equation. When I say increasing the complexity of a model, means that I am introducing additional variables equations. This is the meaning of a mathematical model. A system of equations in a number that allows me to make number of equations and number of unknowns equal, with, of course, some additional assumptions that equations are independent, each other, etc. So this is the meaning of mathematical model. And therefore you see that it's nothing complicated. I hope that I was clear enough. If not, ask me. In order to prove to you that from a very simple technical problem, describing the river flow, I have to go back to another simple technical question. What are the states of my system that I want to consider? How many state variables I need? In this case, I am concluding that I want to take into account the condition of the catchment in terms of wetness, and therefore I need an additional state variable. And therefore my conclusion in this simple case is that I need two equations. Because the input is known, as I said, I have two unknowns. Okay. And then the next question is what kind of equations? In order to understand, first of all, everything is clear so far? Let's hope so. In order to understand what kind of equations, in order to decide what kind of equation, I have, again, to use my knowledge of what happens there. What am I describing here? I am describing movement of water. Water that moves. So, what is the science, the discipline that describes movement of water? It's fluid mechanics. Okay. So I go to Wikipedia and I look for fluid mechanics. What is fluid mechanics? Okay, fluid mechanics, I find on Wikipedia a long description, but what I learned from there is that it obeys to, it's a physical discipline. It obeys to the law of physics. And in particular, fluid mechanics obeys to Newton's laws. Newton's laws, what does it mean? It implies conservation of energy. So, I think at movement of water, fluid mechanics, I look at Wikipedia and I learned that fluid mechanics obeys to the conservation of energy. Perfect. Then conservation of energy is one possible equation. Perfect. A second physical law fluid mechanics obeys to is conservation of mass. Perfect. Let me say, to be more precise then, that we identify two laws that we can use, conservation of mass and conservation of energy. Let me say, to be more rigorous, that actually I should say, for the conservation of energy, I should say conservation of momentum, which is more general. Momentum is quantità di moto in Italian. And in English, it's basically momentum is the conservation of, for a given particle, for a given body, moving body, and in this case the moving body is a drop of water. For a given drop of water, the conservation of momentum means momentum is the product of mass times velocity. And this, it's a vector, momentum is a vector. So for this reason I say that momentum is more general with respect to energy. Energy is scalar. So, It can be proved, but we don't go into the details of fluid mechanics, that for the case of rivers and river flow, in particular, conservation of momentum is equivalent to conservation of energy. But this is a detail of fluid mechanics we are not strictly interested in. Okay. So let's try to think about conservation of mass and conservation of energy. You know that conservation laws should be applied to, for the case of fluid mechanics, to a control volume. Meaning that you need to apply these laws for the case of fluid mechanics to a portion of space, can be moving or fixed. Let's suppose that is fixed, and inside this portion of space, which is a volume, you have to apply conservation of mass and conservation of energy. And if you think about a catchment, the ideal control volume to which we have to apply this conservation laws is the catchment itself. The catchment is a surface, not a volume. In order to make it consistent, the catchment with a volume, so in order to make consistent what I'm saying, you need to include in the catchment the underground where water is flowing, and it becomes a volume. If you think about a river, it's clear what is the volume. It's the volume of the flow that you are considering. Typically in a river you model between two cross sections. Typically you get a bridge upstream, a bridge downstream, and then you have a volume of water between the two bridges, and this is your control volume. With respect to a catchment, of course, you have to extend beyond the river network. You get the whole catchment area and also the underground where water flows. And we have to apply conservation of mass and conservation of energy there. And you may think, this is very complicated. Actually, it is, but if we introduce some assumptions, it becomes possibly simple. Okay, now just to say something more technical, any catchment is an area that we indicate with the symbol A, usually. How to identify a catchment? Typically, you follow the divide. So you start from the closure, and you follow the divide between two hill slopes. One hill slope that flows towards the catchment, toward the river that I'm considering, and the other hill slope that flows in another direction. You get the topographical divide, you follow the topographical divide and identify the catchment. Keep in mind that if you look at a section, the catchment is done like this. Here you have your river, and here you have a mountain. And therefore, the divide is here. So, rainfall that is falling here, you assume that flows along the surface here, at the end into the river. Rainfall that flows here goes somewhere else. Perfect. But think about the situation where you have a rocky layer displaced in this way. What happens here? It happens that if you have rain here, then rainfall may infiltrate if the soil is permeable, and then when infiltration reaches the rocky layer, you have a situation like this. So basically, if you take as a catchment boundary the divide, you are underestimating the flow to this river, because you have an underground catchment divide that is not the same as the surface catchment divide. So when we estimate the area of a catchment, there is some uncertainty. There is also some uncertainty when we observe river flows and we observe rainfall. Uncertainty is a constant of water resources management. It's a constant of sustainability. You have, of course, uncertainty also in structural mechanics, in economics, but the uncertainty that you have in environmental management in general, it is typically higher and higher than the uncertainty in the other branches of engineering. And this is a concept that you need to deliver to your stakeholders, to your customers. Any client of an engineer expects some uncertainty. Even when we design a house, of course, we try to make the house resilient against earthquakes. So we make statistics, and then we design the house with some uncertainty, because an earthquake bigger than the previous one may happen. So our customer is used to some uncertainty, but he is very confident that an earthquake that is bigger than the previous one will never happen. And you know, during the lifetime of an house, given that we have observations of earthquakes that are very long lasting, like from 500 years ago, in some cases even more, and then we design a house with an expected lifetime of 50 years, there is uncertainty. So it may happen in the next 50 years, an earthquake in Bologna that never happened in the past 1,000 years. But you understand that it's unlikely. So you are aware as a client that there is uncertainty, but also you are aware that this uncertainty is limited. Our clients tend to assume that the situation is the same if we design a water supply system. It's completely different. There is uncertainty, and the uncertainty is very high, because river flow observations start 100 years ago in most of the cases, if we are lucky. In some cases they started 20 years ago. So our knowledge of this system that we call catchment is much lower with respect to our knowledge of tectonics, of earthquakes. And therefore the uncertainty in water resources management, again, it's very relevant. And you have to make this clear to your customer, because otherwise it's like the uncertainty in climate projections. It's not made clear. We are told that in 100 years we will have an increase in temperature, in global temperature of 2 degrees, and people tend to assume that this is granted for sure. Actually, there is a lot of uncertainty. And we need to make it clear, otherwise we may lose credibility. Okay, so let's go back to the area of the catchment. This is an essential information. Why is that? Because we need to define a control volume. And therefore, I told you that our control volume in the catchment is A, needs to be defined as better as we can. If you don't have any additional information to geology, okay, let's follow the line. Now, let's try to talk about rainfall runoff models. And let me start. I think that at this stage I need to introduce some examples. So let me start introducing models. And you will understand how the models that I am introducing are related to conservation of mass and conservation of energy. I think this is the faster way of getting familiar with these models. Because at the end of the story, in a week from now, I would like to apply one of them. So let's try to get rapidly familiar with rainfall runoff models and how they work. And let me start with a very brief mention to the first model that was proposed. Conventionally, we assume that this is the first model. Before I move forward, let me say one historical remark. This conceptual scheme, rainfall that originates river flows, may seem to you very trivial, like, okay, you spent 1 hour talking about something that is very clear, very trivial. Okay, keep in mind that people understood that river flow is originated by rainfall only around 1600 in Italy, and I already told you this. In the past, they didn't realize, before 1600, before 400 years ago, they didn't realize that the river flow was mainly originated by rainfall. Because they had no communication, they thought that the river flow was mainly originating from groundwater. In some cases it is, but very isolated cases. And therefore, the overall conceptual structure is relatively new. And the first model, as I say, conventionally, it is assumed to be the rational formula, which I think it is a good example, even if the rational formula, it's not described in detail in my web pages because it's not used in water resources management. The rational formula is used to estimate design floods. So it's used for dealing with floods typically, not for dealing with water resources management. Still, I think it is a good example, and I would like to spend 5 minutes on it. And the rational formula, it is conceived not for estimating a whole hydrograph. The hydrograph, I would like to remind you that it's a plot of river flow with respect to time. This is an hydrograph. The rational formula, it has been conceived for estimating the peak flow of an hydrograph. Let's call it QP. Why only the peak? Because it's easier. They had to propose a model that was simple. It was proposed in 1859. So they didn't have any computer, they didn't have any, they